session.
Okay, can you see my slides?
Yeah, wonderful. Thank you. Okay, I'll leave it to you.
Thank you very much. Thank you very much, Feliciano and everybody for organizing this very nice tutorial. I'm happy to be here and to be able to present a bit more practically how to run Wannier90, the code we're going to see today, which will be the kind of first part we will need to use to be able to run EPW later. And in particular, to kind of introduce you to the tutorial you're going to do in the next couple of hours. The first thing I wanted to mention that actually the main person who spent most of the time preparing the tutorial is really Junfeng Chao, who is actually here and will be helping you throughout the tutorial together with me and other tutors in an hour. And so the other thing I wanted to say, so what I'm going to do now is to give you a presentation, I think on the program is about 50 minutes, about the code itself, Wannier90, and a bit of introduction to the exercises you're going to do. And there will be essentially a first part, which is more like softer. So maybe for you, it's early in the morning. For me, it's late in the evening. So also going to be softer for me. So I'm introducing a bit the code, the community, etc. Nicola already mentioned a lot of this. There will be a central part where we have also some theory instead on the SCDM method. So just so depending on interest, you will have a soft part, a bit harder theory part, and again, a soft part at the end. So just you know a bit how the intensity of the talk will be. So let me start with the kind of soft part, which is about the code. So the code is called Wannier90, and the website is the one you see on the top here, which is www.wannier.org. So I'm going to present a bit the code. You will find it already compiled in the location Feliciano mentioned earlier. But this is mostly if you want to use it yourself later in your computer, in your supercomputer. So you go here, and I just going to mention a few important things. So the most recent version is version 3.1.0. It's actually now 1 year old, but that's mostly because the code is relatively stable, I would say. So there have not been major changes since then. The other thing I wanted to mention is that if you want to get the code, you can very often you can install it directly with Quantum Espresso. But since Wannier90 is not necessarily bound to be used with Quantum Espresso as an interface with many other codes, many other ab initio codes, you can actually just download it from here. You can find a tar zip, or you can, if you are more into the development side, you can just go on GitHub and get the code from directly from GitHub, so you can get the most recent version with the latest bugs fixed and install it from there. The other thing which is very important, I think, is documentation and support. So in the support section of the website, you will find a number of very, very useful resources. The first one, which I really recommend you download, maybe don't print it, it's a lot of pages, it's a lot of trees, but maybe keep the PDF on your computer, is the user guide. The user guide is very, very long and explains every variable one by one, is detailed here. There is an explanation of what it means, the units, how to write it with examples, and all the possible flags and explanation how the code works. So really, if you now in the tutorial or later, you find a flag, you don't really know what it means, just go to this website, support, user guide, and you search for your flag, and you will find a very extensive documentation. The other very useful part is actually the examples and tutorials. Actually, the tutorials we will be running today are mostly taken from existing tutorials. There is one new, essentially, but the other ones are the same or modifications from the examples you find in the tutorial. And in this tutorial, you will find about 35 or 40, I think nowadays, different examples from very simple, as we see today, silicon valence, silicon conduction, to quite advanced. So there is a tutorial for essentially every advanced feature in the code. I saw before a question about symmetry in Wannier functions, and there is a method about symmetry adapted Wannier functions, and there is an example about that. There is an example about to use magnetization, an example about using essentially any feature which is now available in the code. And the nice thing is that beside the tutorial itself, so the PDF is the instructions, and the actual files are in the code itself. There is an examples folder, but it's explained. Actually, last year, a colleague who is also one of the co-authors of Wannier90 Valerio Vitale wrote a very extensive booklet of solutions. So for every exercise, apart from the very recent ones, there is an extensive solution with figures, plots, and all the results you expect to find. So that's also very convenient if you want to run the tutorials yourself and you have some doubts, you can go there and see what the expected result is supposed to be. The second part, which is very important also about support, is how to get help. And how to get help, the suggested way for the Wannier code is to subscribe to the mailing list. You just go here, you subscribe with this link, and then when you want to ask a question, let's say, you can write an email to this mailing list, and everybody receives, and whoever knows the answer can answer. And so the mailing list is relatively low traffic. There will be maybe one or two emails a week, typically not very, doesn't have a lot of traffic. The very important suggestion is there are archives. So we've passed requests to the mailing list, and since 95% of the requests typically are always the same, I really strongly suggest that you first search in the archives if the question you have has already been answered. Just because otherwise, people will end up always answering the same questions. It just takes you maybe 30 seconds to check, and you spare minutes and minutes of time to reply. But this will mean that essentially you first have a place where you have a lot of answers already. You just go and search in the archives, and there's a link here. Or you can ask questions if you have any. And then the other important thing I wanted to mention is that you can go here and see which papers either describe the code or describe important methods which are implemented in the code. And one important thing I wanted to mention, especially to those of you who already used Wannier90, but actually for all of you, there is the new paper which has been published last year. And if you use a recent version of Wannier90, so 3.x, 3.0, 3.1, I would really strongly suggest that you use you cite this new paper and not the earlier ones. So maybe if you have been keeping a BibTeX you copy paste for your publications, please update it and use this new paper. The reason being that a lot of new people have been contributing to the code. So this is the kind of team of people who is currently, let's say, actively maintaining the code, as the people who have mentioned before by Nicola. But there is a larger number of people who are actually the co-authors of the Wannier90 paper, the latest one, who are actually contributing very often in very significant ways to make the code what it is today, to contribute new features, to contribute improve testing to make sure the code is more robust and more reliable, to improve the documentation, etc. So by citing the new paper, you really acknowledge the hard work of all these co-authors, which have been essential to make Wannier90 what now we call a community code. And the community code, because the code is now has been for the past few years hosted on GitHub. So not only the code is open source, but really you can contribute to the code. So if you find a bug, we strongly encourage you to go and open an issue, and even better, if you know how to do it, to go into the code and fix it and provide a pull request. This will make, so the bug you fixed will make life easier to all other users, and we strongly encourage you to do this. It's super welcome. And even if you are not sure, try, and we will tell you if maybe there is a different way to do it. We can tell you how to do it. But in this way, you become really a contributor. So you find this code, which is this is true for Wannier90, but it's true for Quantum Espresso, it's true for EPW. For all these open source codes, you get a code for free, which is the work of years of developers, years of researchers, and your little effort can really pay off and make the code better for everybody. So really, again, a strong encouragement for open source software is very nice, and a little effort of everybody can really make software even better. Now, moving a bit into the code itself. Now, maybe some of you already know the code or have been using the code in the past, but in this 3.0 release in particular, there have been a number of nice new features which have been implemented, are now available in the code. And so here I just put a couple of screenshots from the website where we list all the features which are currently implemented. And for each feature, there is a reference to the paper where the method has been described. So again, if you use the code, you want to cite the code, but of course you might want also to cite the actual paper in which the method has been developed. And so beside the kind of standard things, the things which have been there from the very beginning, implemented by Nicola and by David Vanderbilt in the beginning, and then Ivo Souza for the disentanglement, and then all the work of Arash and Jonathan to implement in the new code. You have a number of new features which are now there, including, for instance, just list I highlighted here in red just the kind of more recent, not because they're more important, just because they're more recent. You have, for instance, symmetry adapted Wannier functions, which is a method to enforce symmetry on the Wannier functions based on the point group of the specific decompositions of the atoms. So you want something like which is S like here, P like there. You can do it with this method. And this will not see. There are tutorials. So again, you can go and the link I was showing you before, and you can look at the tutorials if you're interested. We won't see this today. The other method, which you actually will see if you have time, is the SCDM method. So the SCDM method is a method to essentially avoid to define initial projections. As you, I will discuss this in a moment. This is the part which I will discuss more theoretically, let's say in about 5 to 10 minutes. But as you saw before from Nicola's talk, in order to start the minimization, the code will typically, as typically required in the past, an initial projection. So you say, I expect to have S orbitals there, P orbitals here, or maybe an sp3 hybridized set of orbitals on this specific site, etc. And if you tried already, you would know that if you don't put the right projections, it's very hard to get the right Wannier functions. They might get wrong, and it might not be real. The interpolation might be wrong. And instead with this method, this kind of automates most of the work, maybe not 100%, but then 95% of the work to define initial projections. And what we did in a recent work, which I'm going to mention in a moment, we also automated the final, there are a few now numerical parameters that have to be selected, and this is what we show in a moment, and we see in the tutorial how you can select them. But essentially, there is a method to compute Wannier functions without having to provide explicitly the initial projections, making it very easy to use for automation, for instance. If you're a material, you just want to know what the Wannier functions are. Another technical but very important feature is that since version 3.0, the code is now parallel. So you can take use of MPI parallelization. Now, with respect to a DFT code, the Wannier code typically takes much less time. It's much less expensive. You have a basis set which is of the order of the number of Wannier functions you have. So you don't have, thousands of plain waves. You typically have tens of Wannier functions. Still, many calculations can be parallelized, and so the current version of the code can run in parallel. That's very important, and what we see also later. Now, there are, this is the second half, let's say, of the features you will find on the website. And again, I mentioned a few interesting features. There are many more. So one is there are a number of plotting routines, density of states, etc. One interesting thing is that if you run GW calculations, so like with the Yambo code, it's now possible through some scripts which are provided together with Wannier90 to produce a Wannier interpolation of the band structure using GW corrected bands. That's very important because when you do GW correction, typically you get only the correction on a few points in the Boolean zone. Thanks to the interpolation of the Wannier functions, you are now able to look at them throughout the Boolean zone. There is another module which is about Berry phase related properties, which includes all the properties you see here: Berry curvature, anomalous Hawk conductivity, orbital magnetization, shift currents, and geotropic effects. These are described in the paper itself, the 2020 paper of Wannier90, but also in the respective references. And so if you're interested in topological properties in general, there are many things which are already implemented. And then there are a number of transport properties which the code can compute. And these include transport in the Boltzmann transport approximation with a constant relaxation time. You will see actually in EPW there is a better approximation to this, but if you want a quick and dirty result, let's say you can use already this module. And spinol conductivity is another property you can compute using Wannier90. So this kind of concludes the very, very first part of my presentation on the code itself and which properties it has, what you can compute, and where you find information. Again, always go to the website. And now the second part will be a bit still kind of not very deep, but a very brief introduction on how a typical calculation with Wannier90 looks like. So what are really the steps you need to do? What are really the files that will be created? As Nicola explained, there are a number of matrices the code needs in order to compute Wannier functions. And in particular, there are two sets of matrices, what are called the MMN matrices and the AMN matrices. So the MMN matrices are overlap matrices of the periodic part of the wave functions at point K in the zone, and the point K plus B, so in one of the neighboring points in your grid. And MN are just the indices on the bands. And so these are essential input. The other very important input is the AMN, which is essentially the initial projection. So you say, I want an S orbital, so the code will the interface code. So there will be a code between Quantum Espresso and Wannier90 will produce these files and will tell essentially where to start the minimization from. The best starting point is what Nicola called these Pullman Wannier functions are given by these initial projections. And actually the methods like SCDM, which essentially avoid you to have to define initial projections. What they will do essentially is to create in a clever way these AMN matrices so the Wannier90 code knows where to start the minimization from. So these two files are critical and you need to create them with an interface code between your ab initio code, we will see Quantum Espresso, and Wannier90. The nice thing is that Nicola and then the code, they define this format of MMN and AMN in such a way that any ab initio code can produce the file in the same format so that Wannier90 is always the same. So Wannier90 will always read the same MMN and AMN independent of which code it produced, what they were produced from. And then it's just the role of, let's say, Quantum Espresso, VASP, Siesta, etc., to produce these files in the right format, because creating them depends on the basis set you use. If you have a plane wave basis set, you have to compute the quantities in a given way. If you have a localized basis set, you compute it in a different way. But the format is always the same, and the format is also described in the documentation. In addition, very often you will need a list of eigenvalues, so the band energies in the points K computed by DFT. And if you want to plot Wannier functions in real space, you also need the periodic part of the wave functions U and K in real space to plot them. And so the way to do this is that you first compute the wave functions on a grid using, let's say in our case, Quantum Espresso. And then you use an interface code, and we'll show in a moment the exact steps, to compute these quantities, and then you run Wannier90 with them. So you get the Wannier functions. One important reminder, we'll find the link also in the PDF of this first tutorial, is that if you have doubts about the flags of Quantum Espresso instead, you can go in this link. So for Wannier90, I showed where the flags are. For Quantum Espresso, you find all the explanation on this link. And we essentially will assume you know Quantum Espresso. We will provide you already the files. I will just show in a moment very briefly how an input file of Quantum Espresso looks like if you never saw it. But I mean, we will not do a tutorial really on Quantum Espresso. We just start on the Wannier90 part. But if you have specific questions, you're happy to please ask later to the tutorial. So that's how a typical flow of workflow, if you want, of a calculation works. And this is quite specific to Quantum Espresso, but it's not very different from other codes. So the first thing you want to do is to do maybe a relaxation first, but then an SCF calculation. So you want to compute the ground state density, charge density, on a converged parameter set and a converged set of K points. And this you typically do using symmetry. So you only compute K points in an irreducible wedge. Once you do this, you have the charge density. And so you can use it to do non-self-consistent calculation and SCF. So you run again pw.x with this different flag, which you just compute the wave functions on the K points you will give it, using the same charge density you already computed. So this is faster. But because of the way Wannier90 is written, you will need to do it on a complete K mesh. So if you want a 4x4x4 mesh, you will have to compute all 64 K points. So that's a difference. So first of all, the K grid might be different. On the first step, you want a K mesh, which is converged to get the right charge density. On the second one, you want to compute on a different K-mesh, which is expanded for symmetry, all the points, and maybe different. Maybe you need more or less K-points, depending. So here you don't want any, you have the charge density that's converged. What you want to do is to converge essentially, for instance, the center and the spread of the Wannier functions. So there are two different parameters in a sense. Sometimes they're similar, but you might want to converge them independently. Now, at this point, after you have the wave functions on all the points, you still don't have the inputs of Wannier90. You still need this AMN, but this can be computed easily, let's say, quotation mark, from the wave function. So the first step is to call Wannier90 in a pre-process mode. So you pass a -pp flag. This will read your Wannier90 file, and we create a temporary file called NNKP, which is needed in the next step to compute the AMN. And so this is just this takes a fraction of a second, super quick, produces this file. And now, let's say the first important thing, the last thing which has to be done before actually running Wannier90. Every code has an interface code. In the case of Quantum Espresso, it's called PW to Wannier90, but other codes do it in a different way, which is the interface program, which will read the wave functions you computed on a grid. And the information you put in this Wannier90 file, which will be put here, which essentially will which projections you want, which K-points you use, etc. And we'll do the computation and produce all the files that Wannier90 needs. So MN, AMN, these are the two matrices sets. Eig for eigenvectors, eigenvalues, sorry. This is the band energies in the points that were computed with FT, etc. And some, depending on what you compute, there might be more files. At this point, Wannier90 has all the inputs it needs, and so you can just run Wannier90.x, and this will read all this information, we'll read the Wannier90 input file, and we'll do all the calculations. We'll first do the minimization step, possibly we'll also before do the disentanglement step. And then, depending on what you ask, we'll also compute the properties. And there is sometimes also a post-Wannier90 code, which will compute some properties afterwards, which we'll not see today. But you can many of the properties I mentioned before, like transport, etc., are computed in a next step. In parallel to this, you can also compute the DFT bands, because very often one important criterion to decide whether your Wannierization is good or not is to compare the interpolated band structure. So you compute the bands with DFT in a very coarse set of points. You interpolate with Wannier90. You interpolate the band structure and you plot it. Then just the band structure, you might want to plot the DFT band structure in a denser grid and compare to see if the bands are the same or not. If they're the same, your Wannierization is good. If they are different, your Wannierization wasn't so good. And so the way to do it is to run another pw.x, this time using the K-points on a path. So this was an SCF where you computed on a full grid without symmetries. Here you would have another SCF on a path, let's say from gamma to X to L, etc. And then you run these two codes, which create essentially a plot for you. And just an important warning, as a practical warning, you don't want to mix the green path and the yellow path. Just because in these 2 points, the NSCF will overwrite the wave function. So if you start running the green one and then maybe start the yellow one and go back, you might have problems because this step will overwrite the output of this and vice versa. So you want either to quickly do this, get the DFT bands, and then continue with the NSCF, etc. here, or you first finish the Wannierization and at the end you do the DFT bands. Just a word of warning so you don't, let's say, have obvious problems when you run your tutorial. Now, going on, a bit more practically in the exercises we give you. First of all, you will have 5 exercises. And we tried, since we didn't know what's your previous experience with Wannier90, Junfeng and me tried to be as general as possible, trying to address both people who never run Wannier90, but also people who are relatively experienced. So we have, I would say, the full range of exercises. So if you never use Wannier90, or if you use it, you forgot everything, I'd say, you can just start from the beginning, and you should do at least exercise 1 and 2, and if you manage, also exercise 3. The rest will be optional. And so the exercise, so the important thing is not, you don't have to do all 5 exercises. You probably won't manage in 2 hours. You should just start from depending on your level. So exercise 1 and 2, I'll discuss in a moment, are silicon valence band and silicon valence and conduction band. If you have time, or if you are a bit more experienced, you already run silicon, but not much more, then I would say go directly to exercise 3, unless you want to remind yourself how silicon works. And in exercise 3, we'll see lead, which is a material we also see in the tutorial in the next 2 days. And you will compute the band structure and also plot the Fermi surface. And now if you're an experienced user instead, or if you are new but very fast, the last 2 exercises are a bit more advanced. So exercise 4 will be again lead, it's the same thing, but we will show you step by step how to use this method I was mentioning, SCDM, to automatically choose the projections. And not only that, but also what is the protocol we devised to choose all the parameters that the SCDM warrants. And then we're going to describe this in a moment. So don't worry, this is just to tell you where you should start. Then we'll tell you each exercise what you have to do. And exercise 5 is actually simpler in a sense. So if you want after 3, if you're not interested, you can go directly to 5. They are all independent anyway. Is Wannier functions for a slightly more interesting material, baron titanate, which is a ferroelectric, to see how Wannier functions of a different material, which is not silicon, look like. And here you have some references, which I mentioned in a moment. So 1 and 2 are references of the SCDM method itself. And reference 3 is instead the method we developed to decide automatically the SCDM parameters. So now I'm going to go very briefly one by one through the exercises, but I will spend the theory part I was mentioning for exercise 4. So 1, 2, and 3 will be quick. Then if you want to tune in for the theory, please take up a coffee and be ready, because I will do some interesting theory to tell you in, say, 5 to 10 slides all you need to know about SCDM. Let's see if I manage. And then exercise 5 will be very quick, and then we are done and we can start the tutorial. So exercise 1 and 2, this is, say, the real basic one, the hello world of DFT and the hello world of Wannier functions. What you will do is to compute the Wannier functions for silicon. What you will do is to plot it. We start with exercise 1, just the valence bands. You will compare with DFT. You will plot them in real space, and you will compare the band structure. And exercise 2 is an extension of them to also look at the conduction bands. For the plotting part, there are some instructions on the PDF, so we'll try to help if there are issues. On the supercomputer, you have GNUplot. If you're not in the US, I don't know if you're in the US, definitely if you're not in the US, doing SSH with X tunneling to see the graphical window is a bit slow. Setup is low, I would say, but still a bit slow. If you have the possibility to install these codes, and in particular the 3D visualization software on your computer, that's better, because then things are faster. Just copy the files on your computer, and you can do the 3D plots, because this will not be easy to do directly from the supercomputer. And this is the only slide I have on Quantum Espresso, essentially. So in case you know Quantum Espresso, it's okay, better. If you never saw Quantum Espresso, hopefully you saw some other DFT code. So I just wanted to give you a bit of names and look at how the input file is written. So these things are called name lists, each group of this. And these are essentially groups of variables. So you say the first group is about the type of, you control the calculation. You say, I want an SCF or an SCF. And you say essentially where the pseudo potentials are, where you want to vary the input and the output, the output files, and if you want to start from scratch or restart. The second one is more about the definition of your system. So IBRAV, which I think Paolo already explained. So, but anyway, it's described in the documentation. So it's the type of lattice you have, Brovè lattice, how many atoms you have, how many type of atoms you have, and the cutoffs. And then you have a section about how you want to converge the electronic structure. So in this case, I'm just defining the convergence threshold for the charge density calculation. And finally, you have a section where you define the type of atoms that are called species, the mass, which is not really needed for an SCF, is important for phonons, and the name of the pseudopotential file. Then you define the atomic positions. You have different way of defining them. Again, go in the documentation if you never saw it. For each atom, you define 3 coordinates, either in relative or crystal coordinates, or you can also define them in angstrom or in crystalline coordinates. You define how many points you want. Here, for instance, you say 10 by 10 by 10 K points. And 0, 0, 0 means don't shift. So include also gamma. And finally, if you use IBRAV 0, you have to also say what is your cell. And here I'm defining, for instance, the cell in Bohr, and that's FCC cell. If you try to write it down, that's an FCC cell. So just a quick reminder for those of you who already know, or a brief introduction to how the quantum espresso input file works. And essentially, you run this, you will compute the charge density for this specific system with these cutoffs. Now, if you never use quantum espresso, one useful thing which we put online in the group, I think a year ago roughly, and now we are always constantly improving, is what we call the quantum espresso input generator. So let's say you have a crystal structure in some format, maybe CIF, maybe XSF or whatever. You can just go in this URL, upload your structure, choose just a few parameters, essentially, okay, the format of the file, if you want PBE or PBE sol, and which set of pseudopotentials you want. That's a library which in the group has been developed, which are tested pseudopotentials. If you think your system is metallic or not, is magnetic or not, and if you want a fine or average or very coarse grid of points. And if you want to refine the cell, so if your cell is not exactly, you have some numerical noise, maybe you can refine it and make it exactly cubic, exactly tetragonal, etc. And once you click on this button, the code in a fraction of a second will return you a full input file of Quantum Espresso with all the parameters already set in a kind of optimal way. I mean, we cannot promise they are perfect for your calculation. You still have to do convergence because these are kind of optimal for simple SCF. If you want to do phonons, maybe you have to increase the parameters. But already they are quite converged, both in terms of cutoffs and K-mesh. You can download directly the file and the pseudopotentials, and you directly get also the papers to cite if you use those pseudopotentials. And you also get at the bottom a visualizer of the structure. So it's also actually, you will use it in the exercise to visualize a crystal structure. Because, by the way, you can also import an existing Quantum Espresso input. So even if you already have a Quantum Espresso input, you can just put it there. It will essentially reuse just the structure and rewrite it. So you can check, for instance, if the cutoffs you had were the same we suggest or not. So this is very interesting, not only for visualizing the crystal structures now, but also for your research. If you have a structure you want to quickly get a good starting point for. I mean, again, please do the convergence study anyway. But these are a good starting point if you want to study your material. And if you find something which you don't like for some reason, you think is wrong, just write to us. There is a link to provide feedback if you think some parameters are wrong, etc. So this is the part about Quantum Espresso. So let's now go and look instead a bit better into the Wannier part. And so when you run Wannier90, instead, so you don't run any more pw.x, but you run Wannier90.x. And as I mentioned earlier, you have to run it twice. The first time is in -pp, so the pre-process step. And the second time without it, you just run for the actual vanarization. The first one is very quick, less than a second. The second one can take seconds, minutes, depending on your system. And if your file name has to end with .win, you can either write x1.win or just x1. But the important thing is that your file has to finish with .win or win, which stands for Wannier input. The input format is even simpler than Quantum Espresso. There are no name lists, but just a set of variables which are on this format, variable equal to number or value. Or you can, it's quite flexible. You can also use a colon instead of an equal. And for variables which are actually require more than one number, you can just put them separated by space. And for some quantities, you need actually to define them in a block. Like if you have to define atomic positions, you will define a block which is defined by begin and end. And in between, you have a name of a block. And in between, you have the actual value. In this case, you are defining two silicon atoms, one in the origin and one in this position. And the other thing which is different, so this is important to remember, the other thing which is different from Quantum Espresso are the default units, which unless you specify differently, the lengths are all in angstrom, while the default, let's say in Quantum Espresso is Bohr. You can say Bohr in Wannier90, you have to write it. And energies are in electron volts. So again, this is different because Quantum Espresso will print in Rydberg, other codes will print in Bohr, but that's the units which are used in Wannier90. So when you want to plot and compare results, you have to remember to convert the units sometimes, and it's important to know. So here I'm going to show you very briefly how the input file for the first exercise looked like. So we decided on purpose not to give you the final file, otherwise you would just run them all and maybe without thinking too much. So Quantum Espresso, you have the full file, but the Wannier90 file, you have some X values and you have to replace them. I mean, it's not very complex, but you just have to put a few numbers. And actually, Junfeng will do it with you, so you're not left to yourself. But in this way, you will do the steps you have to do anyway when running your Wannier90 calculations. I will not spoil the results here, so maybe I'll give you some seconds to think, and maybe anyway Junfeng will help you. I just want to mention, so I don't want to discuss the values here, but I want to discuss more the flags. So the first flag you see is the number of bands. This is the number of bands that were computed in your DFT code. So in your NSCF, if you want to compute, let's say, the valence and conduction bands of silicon, you might want to, you will want to compute maybe 8 Wannier functions. This is actually the second number here, number of Wannier functions, because maybe you want to do sp3 on each atom. So it's 8, sp3 on one atom, sp3 on another atom is 4 plus 4, 8. So this will be your number of Wannier functions. But the bands are entangled. So typically you want to compute more bands in DFT, 12, 16, and then you only extract with this entanglement 8. So this number is the number of bands you used in the NSCF, while this number is the number of Wannier functions, which is the same number you used here. So in this case, for instance, exercise 1 will instead be only the valence band of silicon. We are using here 4 Wannier function we see in a moment, so you have to put 4 because we are trying to just reproduce the four valence bands. There are a number of other parameters, like for instance, the number of iterations. So you want to say to the code, iterate for 100 times, is a minimization procedure, and then stop. You can specify this as a comment, okay? So this is not running now, but if you remove the comment, you can just, after you run the long Wannierization, you just want to rerun and plot. You can just say restart just on plotting. And there are a number of things you can plot. For instance, you can do Wannier plot equal to true, which means plot the Wannier functions in real space, for which you need to remember to ask the PW to Wannier90 code to print, to plot on file the UNK, the periodic part. You can say how big the supercell has to be. You can say, please plot me also the interpolated band structure, and you want to say what is the band path from L to gamma and from gamma to X, and you specify the coordinates. Then there's an important block, which is about specifying the projections. Again, I won't go in detail because Junfeng will show you, and there is a extensive tutorial material you have, so you can read it yourself. But you're saying here, essentially, I want S-like projections, S-like orbitals in these 4 points. And then here you specify the K points, which have to be the same you used in the NSCF calculation. So you say something like 4 by 4 by 4, and here you specify the explicit list of points. And Junfeng will show you how to get this list. And finally, you say where the atoms are and what is the cell, okay? Which has to be the same as a Quantum Espresso, otherwise the code will crash. Yeah, and one important thing you see, in general, it's always an angstrom. But in this case, you have a way to say the cell coordinates are in Bohr. You have to say it explicitly, Bohr. So this was exercise 1, and 2 is similar as an extension where you also will modify the input file to do the conduction band as well. Exercise 3, very briefly, is a similar thing, but now for a metal, for lead, where you will learn how to play with the disentanglement frozen window, the outer window, and how to get the band structure interpolated. And also how to interpolate the Fermi surface, which is very important for a number of properties. And one important comment I wanted to give is that it's very important to use Wannier functions, because in order to get a smooth plot, and for the plot is nice, but also to get smoothly interpolated properties, you will see how important this is in EPW, you really need very dense grids. I mean, this was plotted with a 50 by 50 by 50 grid of K points, which is 125,000 points. But if you compute with Wannier90, it takes maybe a few minutes. If you want to compute in DFT, this might take a few months, maybe, depending on the system. Maybe not on lead, not, but I mean, maybe definitely a few days on a powerful supercomputer computer. So you really want to have an efficient way to interpolate it. And Wannier90 is exactly the way. And now we go to the interesting part where we want to spend maybe 10 to 15 minutes before stopping, which is how to automatically obtain the projections using the SCDM method and the protocol we've devised. So the exercise 4 will do again LED. So you already saw the system, you already know how to interpolate it, but this time you will not say, okay, I want these projections, but the code will, so you will find a workflow which defines this all automatically. And so here starts my kind of theoretical part. I will try to be anyway simple and, go to the point, give you more like a intuitive picture of what's going on with some math, hopefully not too much. And the reason is that if you already run it, just before I start, this is an advanced exercise. So if you never run Wannier90, it's better if you start, as I said, from 1, 2, and 3. Still, I suggest you listen to this part, even if you're not maybe have the time to run these exercises today. You can still run in the next 2 days or at home. The files, you can bring them with you, and the codes are fully open and available. So I still think that's very relevant. But anyway, this is an exercise maybe you will do only if you are going pretty fast. So the tricky part of visualization is really to specify these initial projections. It needs a bit of intuition, it needs to have a lot of experience, and indeed, if you go in the Wannier mailing list, in the archives I was mentioning you first, many of the questions are really, okay, how do I choose the projection for this? How do I choose the projection for that? And the answer is, well, nobody will be able to tell you. Even if you ask an experienced person, maybe they have a gut feeling of how it should be, but in the end, they have to try. So, not to discourage you for asking this question, but in a sense, don't expect a magic answer or a person which in 3 seconds will tell you the answer. The answer is try. And the more you try, the more you learn. And the more you learn, the more you know which projections to pick. And so still having an automated way to pick them would be nice. And that's why the SCDM method is starting to be very interesting, because it's a method to kind of help you find the projections automatically. Now, it's not a magic method. For instance, the functions you get don't really satisfy very nicely the symmetries you expect. If you have 5D orbitals, sometimes you get 5 orbitals, which have kind of bumps here and there, kind of look like D, but are not really perfectly nice like spherical harmonics. So still is not a perfect recipe. But still, if you want to get a quick interpolation of a material, but still good, they are a nice method. So let's see how it works. And what I want to tell you is a bit, I don't want that you use it like a black box. I want that you understand at least the basics of the method. And so let's see how it works. So the first concept we need to do, SCDM is for letters, SCDM. And this means selected columns of the density matrix. Okay. So I want to introduce piece by piece. So we start from the density matrix, then we discuss about the columns of the density matrix, and then we discuss how we select them. So let's start with the density matrix. That's a very general concept. It's not specific to Wannier functions. And essentially, if you have a solution in a Hilbert space, you can write a projector, P, on this space. Okay? And this is just this operator. It's the sum on your orthogonal basis set. We will always assume these are orthogonal and orthonormal, actually. And you sum the projector or each of these spaces. These are, in this case, could be the solution you get from the FT. Okay. And the nice thing of this is that it is a projector, and you can prove it's P squared equal to P. It's very easy to prove because of the orthonormality of the psi, and P equal to P star. And in particular, it's also easy to prove that if you take a system, and for simplicity, I will take a system with only one point, gamma. All of this is extended, but just to make it simple, you can think to a molecule or you can think to a big supercell. So I won't put the K index here. And we consider only the valence states, or in a molecule only the occupied states. So if you only sum up to the valence states or up to the HOMO in a molecule, this is really a projector on that subspace. So it's a projector of what I will call the valence subspace. I will use the names of a periodic system, valence and conduction, but this works also for molecules. And so now, what are the columns of this? So now, if you write the psi, like for instance, you would do in quantum espresso, on a grid, so you take your unit cell and you write it on a grid, on your 3-dimensional grid. What you get out for P is a matrix, so you write it in a kind of discretized form, which is Ng times Ng, where Ng is really the number of grid points you have. So if your charge density is written or stored in a 100 by 100 by 100 grid, you have a pretty big matrix in memory. In fact, we never really write them in memory. But you know, what I'm trying to say, this is a very big matrix. And the columns of any matrix are just, you can imagine them as multiplying the matrix by a vector, which is 0, 0, 0, 0, 1 in a location, 0, 0, 0, 0. Okay. If you take a matrix, any matrix, you multiply by this vector, what you get is the corresponding column. So if it's the 7th position, you get the 7th column. Okay. So that's a general linear algebra thing. I mean, nothing very special. If you know how to multiply matrices by vectors, you see this is the definition of a column of a matrix. But the nice thing is that we know P in part. If you take this matrix to be P, there's a projector. Okay. So we're actually, the column of the density matrix is the projection on the valence subspace of this test orbital. And this test orbital is nothing else than a function that is 0 everywhere, except being 1 in a specific location in space. Now, as I said, I chose as a basis set a grid. Okay, so a function which is 0, 0, 0, 1, 0, 0, 0 is in my grid 0 everywhere, except in a point in space where it's 1. So it's an approximation of a delta function in space. And so the columns of the density matrix are nothing else than the projection on the valence subspace of a test orbital, which is a delta in a position in space. And so if you take this intuitively and use also the concept of nearsightedness of the density matrix, which has been introduced back in the 60s by de Cloiseau and then discussed by Walter Kohn, etc., what you're doing is really to take a function which is a delta in one place, so it's clearly localized, okay, it's 1 there and 0 everywhere else, and you project it on the valence state. And this concept, this criterion of nearsightedness of the density matrix will tell you get a function which is a bit smoother, but is still localized. Okay, you don't get something which is fully delocalized in the system. You will still get something which is localized. So the main thing we learned from this slide, hopefully, is that what is the density matrix, but also that the columns of the density matrix are all localized orbitals. We don't know what they are, but they're localized. And so in order to make it more visual, I decided to make a video of this so things become a bit nicer. So let's take a material, silane, okay, SiH4. And I already computed the Wannier functions. They look like this, okay? These are the atoms, Si and hydrogen, and these are the Wannier functions of my system. And what I'm going to, this is going to be a video. So I explain you first what you're going to see, and then we let it start. You see this point is the point in space, which will represent my delta function. So it's the point in space where my test column is 1. So when it's here, I have a vector with 0, 0, 0, and 1 exactly in this point, and then so on. And this point will move and scan through the whole space. And what I will plot as isosurfaces is the column of the density matrix. So this 1 is the point which will move. Will be a 1 here, then 1 here, then 1 here, then 1 here, and we'll move out in space. We'll essentially move in the grid. And what I will plot as isosurface is what I get here as a column. Okay, the corresponding column is a function. Okay, is a orbital. Okay, and I will plot an isosurface of it. And I will use the However, the important thing is these are orbitals which are not normalized. If I take my point and put it in a place where there's no charge density, my column will be fully 0. Okay, so these are orbitals which are not normalized. So I will not only show an isosurface, but I will also show with transparency the magnitude, the norm of this function. So what you see here at this corner, 0, you see nothing because here the norm is 0. So let's start. And hopefully, even if it's Zoom, you see some animation. Hopefully, it's not too laggy. What you see is when the points gets close to a place where we have electrons, you see that we get automatically, the columns have a shape which is not far away from the actual Wannier functions of the system. Okay, and of course, if the point remains very close, okay, you get a shape which is very similar. Just the norm goes a bit lower. No? If maybe I restart. So when the point is here. The point is, let's say here or very close to here. Okay, all of these look the same, just the magnitude is different. Okay, and so we have a lot of columns, which are a lot of localized orbitals. Some are completely 0, some are similar with lower norm, and some are different. They're not, for instance, this and this. So the two when the point switches are different. Okay, are not the same. And so let's move on and. Let's go to the S, the last part of SCDM. So now we have n columns. Some are 0, some are very low norm, some are very high norm. And we know because it's a projector, that all the columns span the full valence band. It's a projector, so if you take all the columns, you take the linear combination of them, you get everything. But what you really want to get is a basis set, so only n. So if you want n Wannier functions, n is small, typically it's 10, 20, it's not 10,000 or 100,000. You want to select only n of these columns. In the case of C-lane, okay, we have a lot of, you have hundreds of thousands of these projections. You only want to get 4, the best 4. And so the selection, how does it work? You want to get the 4, which in a sense are most orthogonal to each other, are more different between them. You don't want to get 2 which are almost the same. You don't want to get something which is almost 0. You want to get 4 which are high norm and as different between them as possible. And the way to define as different is to say as orthogonal as possible. And the nice thing is there is a linear algebra criterion which does this. It's called QRCP. It's a QR decomposition with permutation, which will find the n most orthogonal columns. I won't describe the method. It's a linear algebra you find in LAPACK. But the interesting thing is just to show how it works in 3 dimensions. If you have a bunch of vectors in 3 dimensions, you want to find a basis set. So you have all this bunch of blue vectors. The SCDM, the QRCP will pick one vector here, will actually pick first the one with largest norm. And the second vector will pick one of them of the other in another group. And the third one, since we're trying to pick the most orthogonal one, will not pick another one in the same group, we'll pick one which is orthogonal to it. And so in this case, you want 3 and we'll get you 3. In the case of C-lane, in this more complex space, we'll pick essentially 4 points, which will give you localized orbitals because of the nearsightedness, as orthogonal to each other, so as different to each other, which are very good starting points for the Wannierization. That's how SCDM works. What you do, the final step, you want, these are not orthogonal, so you really do orthogonalization. And thanks to the loading orthogonalization is a mathematical method which essentially preserves as much as possible the localization. That's very good because we don't want them to mix and you get something which is delocalized. I mean, remember, the goal is to get maximally localized Wannier functions. So you want to get something which is non-perfectly orthogonal, is almost orthogonal. You want to orthogonalize them by minimizing the change you do. And that's mathematically, you can prove this a loading algorithm. The algorithm can be extended and it's implemented also for K-points. So let's quickly look at some results because we're getting at the end of my talk. So we did in this paper a study on more than 80 insulators. And as you see from these plots, in essentially 78 out of 80, so 95%, the bands get very good. You see that's a kind of, the red is the Wannier functions, the black is the DFT. And you see in the valence band only, they are the red is on top of the black. Now, what happens is when you have entangled bands. Now, you cannot anymore define only the projection on the valence band. You have to define something more, which is a projection on all the bands you have, but multiplied by a function which will look like this, which is 1 in the valence band, 0 high in energy, and will smoothly change between 1 and 0. In this way, you consider all valence bands and maybe some additional conduction bands, and then at some point you stop considering states with high energy. It's kind of similar to the windows in Wannier function, but it's a bit different, okay? So you are defining a quasi-projector, a quasi-density matrix on this space which contains all the important states you care about, smoothly considers some of the other ones and doesn't consider anything above. And the function we typically use is this error function, which is exactly this. And as you see, there are 2 numerical parameters, the position of the 0 and how fast this goes to 0, this sigma and this mu. In addition, you have a third parameter, which is n, which is the how many Wannier functions you want, okay? So with the SCDM method, which we implemented in Wannier90 and in Quantum Espresso, this you can already run. You can just set these 3 values in the input, and this will work. What you will see in the exercises is also how we can, the algorithm we wrote to decide mu and sigma fully automatically. And mu and sigma are very important because if you do it wrongly, it's the same material, one test material, tantalum sulfide. If you use the correct mu, you get a very good interpolation. But if you get a wrong mu, let's say a too large one, you see the bands, the red bands have nothing to do anymore with the black ones, which are the DFT. So it's important that you pick the right mu, and you can then check if the mu and sigma are correct. How to choose them? Well, very briefly, because I realize I'm getting very late. what you want to do is to compute what we call the projectability. So these are, let's say, all your DFT bands. We plot many of them. And then you take pseudo-atomic orbitals. So you say, okay, I take an s orbital on my atom, like this copper, so say an s orbital on copper, a p orbital on copper, a d orbital on copper, a 2s orbital, let's say, on copper with one node, a 2p orbital on copper, and so on. And again, of course, there are also the core states we don't see. These are really the semi-core and the balance states. And then you project these orbitals onto the wave functions. You compute the square modulus, you sum, and you go define a number. And so for each band, you can define this number, which is going to be 1 if that specific state is fully well represented in this space. And this is typically what happens in low energy. It's going to be 0 for high energy states, because here you have either plane waves or maybe you have 3s, 4s, other states. And it's going to be to 0 in a kind of semi-smooth way, okay? So this is the band structure. The color gray means 0, this projectability is 0, black means 1, intermediate color means intermediate value between 0 and 1. And here you have a similar plot. That's still the energy, and this is the projectability. So for each band, we just plot for its energy, the projectability. So it's something which is, so all these bands have projectability 1. So you have a lot of, these are not 1 point, these are a lot of points here for all these bands. And here in between is something in between, and all these bands again are 0. And this is a plot you will produce during the exercise. And you can compute them relatively easily thanks to the Project-WFC code, which is part of Quantum Espresso, which computes essentially the part inside the modules here. And so the criterion we suggested is the following. So first, you take the pseudo-atomic orbitals. You know it's silicon, you know it's copper, you know how many orbitals you want to have. You compute the projectability, and you plot this thing, and you fit it with the same curve, okay? This is the same functional form of the curve. And you get a mu fit and a sigma fit. And now what you do is not to take mu fit, mu equal, so this is the mu from the fit, this is the sigma of the fit, and you want to pick the mu and sigma of the SCDM. You don't pick the same ones, but you pick the same sigma, but a mu which is shifted down by 3 sigma. And the reason is that essentially you want to get all states here, which have high projectability, you want to get them. But as soon as the projectability goes down, you're getting a lot of states which have wrong characters, something you don't understand. And you want to cut down to 0 their contribution. So you want already, when you start going down to 90%, okay, you want to give a very low weight to the states. You want the states not to be included in the SCDM method. Well, sigma fit, sigma SCDM equal to sigma fit gives you a physical sense of how broad is the band in energy, where you go from full projectability to 0 projectability. So you want to keep the sigma fit, but you want to move down the mu in order to only consider states we really have very high projectability, because these are the ones you care about. So this is a kind of empirical rule. We tested very extensively. We tested it for many different mu and many different sigma for tungsten as a test material. So these are all possible mu and sigma. This line is the line mu minus 3 sigma. And this point is exactly the rule mu fit minus 3 sigma fit. And these two plots show both the spread and the bounce distance. And so you want to have low bounce distance. The bounce distance I introduced in the next slide is how different the DFT bands are from the Wannier90 bands. And so you want something which is green, which is low. So this looks fine. And the spread, you want something which is small, but not too small. If you put too many states, it's a minimization algorithm. You make a very large space in which you search for, you can find a lower minimum. It's like a variational principle. So you also don't want to go too low. And this plot kind of should intuitively tell you that, 3 sigma is not exactly a rule. If you do 2.5, probably works the same, but it goes in the right area, which is when you want to have the right spread and the right low distance. We did this criterion, we implemented it, and we ran for 250 bands. Again, for 95% of them, things go very well, as you see here, also for the conduction band. So it's kind of good because, for automation, now you can run 250 materials without thinking and just run them. We defined a quantity, which is this is always skip because it's just interesting, but you can find in the slides. We defined mathematically the distance between DFT bands and Wannier bands. So the number will tell you in electron volts how different the bands are. You can either find the points where the bands are most different or other average across the whole Brillouin zone. And this plot just tells you that this, for all the 250 materials, we have on average an error, which is, so the maximum error is 50 millielectron volts, so typically relatively small. And it gets better if you have more K points. These different rows are, these are very dense mesh of K points. These are very loose mesh. Definitely you cannot use this. These are interesting. It gives you also a sense of how to converge K points. You want to use 0.2 or 0.15 angstrom inverse to get good results. And with a converged mesh, you get an error maximum in the worst point in the Boolean zone of the order of 30 to 50 electron volts for most materials, and an average error of the order of 5 to 10 millielectron volt. Final notes. So all of this has been automated with AIDA. So if you will see, you will not see AIDA today, but you will do it by hand, all these steps. But if you're interested, please go look about AIDA. There is a tutorial we did last year where all the steps are fully automated. And again, this is work done by Junfeng Chao. So all these kind of very many steps you will run are done in one step. You press a button and you get the Wannier function and everything. What you will do today is do all by hand, and you will do the projectability plot and get the final band structure. Final exercise, cubic boron titanate. Nothing to say except it is a more interesting material. You get Wannier functions which are a bit more interesting. The very final note, so if after the tutorial you want to go home and you want to try the same things, what I suggest you to do is to download the Quantum Mobile. It's a virtual machine you can download locally on your computer. Contains already a number of codes, in particular Quantum Espresso. It contains Wannier90, etc. You just download it. You don't have to think about installing it. You have all the examples. You can also find the workflows I mentioned, because also AIDA is installed. There are visualization tools. So it's very nice if you want to quickly try the codes without having to install them. Of course, if you want to run in production, it's better if you install them properly, let's say, on your supercomputer. And so very final thing. So today, if you have questions, please ask me, Junfeng, and all other tutors. From tomorrow on, a reminder, go on the website, read it and download the user guide, study the tutorials. There are the solutions, so really there is everything for you. Register to the mailing list. You can already do it today. You can first check if there are questions, otherwise you can ask them. And also read the source code. It's a very useful exercise. And maybe you can also discover you can contribute with new features or bug fixes. And I will leave this here now, but for a few seconds, but this is already what Feliciano explained earlier. And maybe I get some questions, I guess, and then we go with Junfeng into the actual tutorial part. Thank you for your attention.
Thank you very much, Giovanni. So I haven't seen direct, let's say, question related to your presentation. I mean, there is one technical question, but maybe then Junfeng can answer it. Maybe I had one question, and then we can move to Junfeng. Could you comment on how good SCDM is in describing the conduction bands, and sort of how far can it do that? Because from what you explained, basically this strongly depends on, you know, on this mu, and this doesn't go very high above the conduction band, I guess.
Yeah, it's a very good question. So exactly, so the SCDM for isolated bands essentially doesn't need any input. Okay, this works very well. I mean, the two which doesn't work is just because the SCDM method has some flaws. But I mean, you know how many bands you want, and there is no parameter. When you go into the conduction bands for a semiconductor, or in general you use a metal, you have these two parameters. And that's really up to you. And actually, when people typically say there are two parameters, but in reality there are three. And there's also one comment is exactly about how to choose the number of Wannier functions. And as I said, the way we suggest to do it is to do this. So you decide essentially how many orbitals you want. Okay. By chemistry, you already know, okay, which are the relevant ones. You know the pseudopotential, so you know which one you don't have to consider at all. Actually, you could also remove some semicores, so you kind of make your simulation cheaper. And then you know, and typically it's also already written in the pseudopotential, how many have been used, for instance, to construct a pseudopotential, which typically include enough bands, high in energy, to represent the bands you care about. You typically anyway don't care about 20 electron volts above the Fermi energy, you care about maybe a few electron volts above the Fermi energy. And by doing the projectability, you already will discover if with these orbitals, you are representing well enough the energy in which you are interested. So in this case, for instance, let's say I use this 1, 2, 3, 4, 5 type of orbitals. These are 1 plus 3 plus 5 plus 1 plus 3. So something of the order, I don't know, 10, 15, I don't know. You do the projectability and discover, okay, that's my Fermi energy. Okay, up to here, so all the one below, have a projectability which is 1 or almost 1. Fine. Then I know that I will be able to find Wannier functions which reproduce my states. And actually, something which even if you don't do SCDM is something very useful to do, because if you discover that your projectability, so your Fermi energy is here, where half of the states are already, 0.5 or lower projectability, you already know probably your Wannierization will be very hard to get. And so once you go here, what you do, you just have to make sure, on the other hand, that you go high enough the bands you can put in DFT. Here you really exaggerated, but I mean, you cannot stop here, let's say. Okay, you cannot stop at 25 because you're cutting away some of the states which still have the character you care about. So you think in the standard way of Wannierization, you want essentially your frozen window to be here. So to be in an energy where still all states are projectability 1. And you want your outer window to be high enough that you take all states which have a projectability almost a bit above 0. Okay, these are all 0, so you don't care. Even the standard disentanglement will not mix them, and it's good not to put them actually, because it might try to put a percentage of this. So you want to stop here, but you want to have the frozen window here or here or here, but not here. Okay, and the same thing for SCDM. So SCDM and our protocol will help you do it in a kind of automatic way. So my suggestion is you do this, and if you discover your Fermi energy is here, you probably means you have to add more orbitals. Okay, in silicon, this typical case we discussed with Samuel, actually, you need to put the orbitals. If you don't put the orbitals, the conduction band doesn't come very well. And you will see in the tutorial, it comes okay, but not perfect. If you said you have, projectability 1 up to here, maybe you put too many orbitals. It's okay, but it's just very expensive. You might want to remove some orbitals. And then when you do SCDM, I mean, typically it works fine. Typically, I mean, typically mean 95% if you use our protocol. It's not perfect, and there are, maybe it becomes a bit technical. I'm happy to discuss later what it means, what are the flows, and again, as Nicola said, with Junfeng, we are working on a different algorithm to make it automatic, which is not based on SCDM.
Thank you very much. Very clear. So there's maybe 2 questions, and then we could move to Junfeng. So the question is it possible to get bond-centered orbital in Wannier90 with SCDM automatically? And then he says, I had to perform rotation manually, which is not convenient.
Yeah, so I replied to this, and also I already see the other question. So no, no, in the sense, SCDM works almost a black box. You run it, and that's what you get. So you have no choice. That's why we are trying to go with Junfeng and Nicola beyond SCDM, because you have no way to decide, for instance, if you want not only where they are, but also, for instance, the symmetry. You get something and you are happy with it. If you just care about band structure interpolation, typically it's okay. If you want to do other things, it's complicated. So you really have to do something else if you want to do, if you want specific properties like centers or symmetry. Still, using SCDM is good because you can give you a hint of where the Wannier functions want to be. But remember also that typically, if you just do Wannier functions in the valence, you typically get bond-centered if you have a covalent bonds. If you do what we're suggesting, what we are trying to give you is atom-centered. So depending on what you choose to do, this will give you different results. The other question I see is, does SCDM provide what the final orbital forms are? So no, in the sense I was telling you, in the sense you don't know what we get, you get something. Typically, because of the protocol we tell you, which is to use this number of orbitals, etc., you typically get something which looks like this, but it's not true. I mean, sometimes you get a mixture of them. On the other hand, you can see what they are because you can use Wannier90 to plot the Wannier function. So at the end, you can plot them and see what they are. And then about symmetries, are there ongoing work to improve these aspects? Yes, as I said, we tried quite hard to improve and combine SCDM with symmetry. It's very hard. It's not really possible. Or at least we didn't manage, let's put it this way. But with Junfeng, we are working on something which is not SCDM, and we hopefully, so we have very promising results. We hope to have a paper soon in a few weeks, a few months, which will essentially give you quite nice properties of the orbitals. which will be based on atomic orbitals, however, not SCDM. Finally, for the question from Yoongjun Lee, so we are only using in the automatic protocol the error function. True. So this I didn't mention. In the original SCDM, there is another way to choose the function, which is not an error function, so from 1 to 0, but is a Gaussian. So allows you to focus only on bands in a specific range. This is very convenient, for instance, when you look only at the D bands in a metal, in copper, let's say, you want to discard the rest. We didn't do it because we had to decide an automatic protocol. And the automatic protocol we wanted to do is to do something based only on the chemistry of the atoms, on the atomic orbitals. So we say, we know the atomic orbitals, we make something automatic from there. You can do a CDM, but it's very hard to make a rule which you also decide, because you have to tell essentially, okay, I'm caring about the orbitals in this range, and then please use a Gaussian. So the automatic protocol will only use the error function. If you don't care about the automatic protocol, you want to experiment, the Wannier code and the Wannier90 code implement also the Gaussian, and you can just put by hand and try mu and sigma. I think this answers all questions.
Okay, thank you. Maybe Junfeng, if he wants to share his screen.